Hello and welcome. Introduction. In this video, I'm going to show you how to program the TM4C123G SysTick Timer using assembly language. So let's take a look at the TM4C123G SysTick Timer. Now, the SysTick Timer is a hardware-based timer built inside the ARM Cortex microcontroller. In our case, our microcontroller is the TM4C123G SysTick. Now, it is a 24-bit countdown timer, and the maximum value that can be loaded into the SysTick timer's load register is to the power of 24 minus 1, which equals to 167777215 or hex FFFFFF. Now, once the timer starts, it counts down from the value loaded into the load register towards 0. We'll come to the load register in a little bit more detail later. When the counter reaches 0, it generates an interrupt. Now, when a SysTick timer interrupt occurs, the nested vectored interrupt controller, or NVIC, transfers the control of the CPU to the corresponding interrupt service routine, or ISR. Now, before I go any further, here is let's take a quick look at the block diagram of the TM4C123G SysTick microcontroller. So this is the high-level block diagram of the microcontroller. Viewers of this channel will have seen this before, but here I would like to focus on the NVIC, which is located here. Now, the NVIC really is a on-chip controller that provides a fast response to interrupts in the TM4C123G SysTick microcontroller or any other ARM Cortex-M based microcontroller. So this is the NVIC in relationship to the processor core, and here is the SysTick timer. And all this, as you've seen earlier, is enclosed inside the processor. And these here represent our various interrupt signals. Vector table. Now, the NVIC uses the vector table to determine the entry point or the address of the interrupt service routine for each interrupt source. Now, each entry in the vector table corresponds to a unique interrupt or exception number. Now, this interrupt number or exception number acts as an index to the table, where the corresponding entry holds the memory address of the ISR, or interrupt service routine. Now, so here is the vector table for the TM4C123G microcontroller, and this table is taken from page 107 of the datasheet of the TM4C123G microcontroller. Notice the SysTick exception number, or interrupt number is 15 or an IRQ number of -1. Now the minus denotes it is an internal interrupt or system exception. SysTick handler. Now the SysTick interrupt handler is a function that gets executed when the SysTick timer reaches 0 and triggers an interrupt. Now the SysTick timer handler function is defined by the programmer to handle specific tasks at regular intervals. SysTick timer registers. Now the SysTick timer is controlled through specific registers. The first one is the SysTick control and status register. This enables and configures the timer. Then there is the STRE load. This is the SysTick reload value register, and the function is to hold the reload value to determine the interval. Then the SysTick current value register. This holds the current count. So this is the SysTick control and status register, or STC-TRL. And I've taken this from page 138 of the datasheet. Now, notice this is the base address and the offset is 010 hexa. Notice this STC TRL register is a 32-bit register, and we are interested only in a few bits here. I will summarize this diagram with this here. So the bits that are of interest to us is 0, bit 0, bit 1, bit 2, and bit 16. Now, I will talk more about this soon. The next register is the SysTick reload value register, and this is the STRELOAD or ST reload. And the base address is here and the offset is here, and this is taken from page 140 of the datasheet. And notice again it's a 32-bit register, and I summarize it with this diagram here. So the reload value register is actually from bit 0 to bit 23. So it is a 24-bit register. Please take note of this. Then finally, we have the SysTick current value register, or ST current. This is the base address again, and here is the offset. And I've taken this from page 141 of the data register. Again, this the data sheet, page 141 of the data sheet. And this is the register. Again, it's a 32-bit register, and I will summarize it here. And the current value basically sits in from bit 0 to bit 23. The program. So at this point, I'm going to show you the full listing of the program, and I will discuss the details of the program in a short while. Okay, so here is the full listing of the code that I'm going to use. As I mentioned earlier, I will just go through a full listing with you first, and then we'll talk about the details in a few moments. So here, basically, I have defined the code section. This is the export directives. This is the entry point of the program. And here I define the registers used in the program. And here are the bit mask that I'm going to use in the program. And here is the start of the main routine on the main program. All right, we carries on. Just to highlight, a few moments ago I mentioned about the SysTick control register. So here, this part here will configure the SysTick control register. This is the load value of the SysTick timer, and here is the current. Here I clear the current value register, and here this part here basically I'm sending it into a loop, and this part here is the SysTick handler routine. So basically that's the full listing. We'll talk about the details after this. Program explanation. Okay, so here is the Arial my code code read only. So this basically define the code section. Code here, my code here is a name given to the section. All right, code indicates that this section contains executable code, and read only means the section is read only and cannot be modified at runtime. And these two are directives. The first one here, export directive, says that _ main is made visible to the linker. And then this export directive here export the SysTick handler to which is the interrupt service routine. And entry is basically the entry point of the program. And then what follows here are the registers definitions. So here, for example, is the system control register for the GPIO clock gating. Then the GPIO F or GPIO port F direction register base address. So this is the base address of the GPIO port F direction register. And then the GPIO F digital enable register, followed by the GPIO-F data register, and then the SysTick reload register, and then the SysTick control and status register, and the SysTick current value register. So these are all the base addresses for these registers. Next comes the definition for the bit mask. So I have defined LED 04 hexa. That is the port F bit 2. That's the blue LED on the TIVA C series launchpad board. Then this here is the for enabling the clock for port F. So the value I've assigned is 20 hexa to this name here, this symbol. And then the SysTick control value, the enable value, 03. Basically, this will enable, this 03 hex will enable the counter, the interrupt, and set the PIOSC clock to using the 16 megahertz, because this PIOSC clock is operating at 16 megahertz. So basically these are the bit mask. Okay, so let me explain why I use a 03 in the SysTick control status register. Now, if we look at this diagram here, which is a summary of this 32-bit register, so the first bit, bit 0, ENB, that's enable, right? This is set to a 1. Oh, by the way, 03 translate to binary is this one here. All right, so ENB is set to 1. Basically, that enables the counter to load the reload value and begins counting down. All right, so this is set to 1. And then this second bit here, bit 1, INTEN, is also set to 1. This is an interrupt enable. So an interrupt is generated to the NVIC when the SysTick counts to 0. All right, so this has to be set to a 1 to enable the interrupt. And then this clock source CLK underscore SRC, this is set to a 0 because I want to use the precision internal oscillator or divided by 4, and count is set to a 0. All right, that means the SysTick timer has not counted to 0 since the last time this bit was read. All right, so that's why I've used 03 hexa in the SysTick control status register. Okay, so we've come to the main routine here. This is only part of it, there are more to come. So let's consider this beginning part. This is this symbol here, or this label here, underscore main proc, signifies the beginning of a routine or procedure, PROC proc. And here, this instructions here, these 3 instructions enclosed in this red box, basically the purpose is to enable the clock for the GPIOF. GPIOF is the GPIO for port F. All right, so these instructions will enable the clock for GPIOF. Now, this label here basically is a name given to a register. The register is assigned this address, which is 400FE608 hexa. All right, so this has been assigned to this label here, which is referring to this register, and basically that's load the SYSCTLRCGC GPIO address, all right, into register R0. And this label here is been assigned or given the value 03 hexa. So this value will be loaded into register R1. And this store instruction here will basically store the current value of R1, which is this value, into not R0 itself, but in the address that is stored in R0, which was assigned here earlier. So it will store the current value of R1 into this address. And basically, like I said earlier, these 3 instructions will enable the clock for the GPIOF. Next are these instructions here. The purpose is to configure the GPIOF direction for port F bit 2, PF2, port F bit 2 as output. So basically, this label here, GPIO F _dir, that has been assigned 400254000 hexa. So this value has been assigned earlier, and this value will be loaded into register R0. Basically, this is the GPIO F direction register base address. Then R1 is been assigned. This is a load instruction. Just like these are all load instructions, they will copy this value, which was given 04 hexa. This was declared earlier, and load this value into R1. Now this LDR instruction will load the contents of the address pointed to by R0. Not the contents of R0, but the address pointed to by R0. So R0 is pointing to 400254000 hexa. So the contents of this memory location will be copied into register R2. And here ORR basically is a bitwise OR operation between R2 and R1, contents of R2 and contents of R1, which is basically these two here. And the purpose is to set PF2 port F bit 2 to a 1. All right, so this instruction here will basically set this PF2 to a 1. The str store instruction will store the current value of R2 into the address pointed to by R0. Now R0 is pointing to this address, so it's 400254000 hexa. So the store instruction will store the current value in R2 into this address. Okay, so next we come to this group of instructions here. Basically, this will enable PF2 as a digital pin. All right, so GPIO-F _DEN, that has been assigned this hex value, that is 4002551C hex. That is the base address of GPIO-DEN. So that value gets loaded, LDR loaded into R0. The LDR instruction here will copy the contents of the address pointed to by R0, and R0 is pointed to this address, that is 4002551C hexa. So the contents of this address, will be stored into register R2. And here is a OR operation, and basically the purpose of this bitwise OR operation is to set PF2 port F bit 2 to a 1, and then that stores, and here the current value of this is stored into the address that is pointed to by R0. That is to store the modified DEN value. Next, we'll come to this group of instructions. Basically, this will configure the SysTick control register, and this label here, this has been assigned this base address. This is to load the SysTick control register base address, which is E000, E010, and copy that or load that into R0. LDR is load, and then this here, this label here is been assigned this value 03 hexa. Basically, the purpose of this is to enable the SysTick, the interrupt, and the system clock. And this value will be copied into R1, and then here the familiar store instruction will store the current value of R1, which is this value, into this address. Okay, so here we have these instructions here that will load the SysTick value. Now this label here has been assigned this hex value E000, E014. That basically is the base address of the SysTick reload register. So that gets copied or loaded into R0. And this value here, 4007500, is decimal. This is in decimal. Load this decimal value. This value is supposed to generate a 1 second delay. Now the exact value, I'll explain that later on during the demonstration. So that gets copied into register R0, and here is the store instruction that will store this value in the SysTick reload register. So the Kill Microvision startup file. Now this only applies to the Kill Microvision IDE. Other IDE will do it differently. So the Kill Microvision startup file sets the system clock of the TM4C launchpad board to 50 megahertz. Now there's a limitation to the SysTick in that if you remember from an earlier discussion, we know that the SysTick reload register is a 24-bit register, so it has a maximum value of FF hexa. Now in decimal, that will be this. That is 16777.215 decimal. Right. So with the 50 megahertz clock, this value is not sufficient to generate a 1 second delay, since it would require a reload value of 50 million. All right, because of the limitation of the 24-bit, we can't have this value. So the solution is to set bit 2 of the SysTick control status register to 0. Bit 2 is the CLK_SRC bit. All right, so we need to set this bit 2 to 0. What effectively that will do, that will select the precision internal oscillator, or PIOSC, divided by 4 as the clock source. Now the PIOSC frequency is 16 megahertz. So this 16 megahertz will be divided by 4. That will give us 4 megahertz. Right? So the SysTick reload value can be set to 4 million. Because of the 16 megahertz divided by 4, that would be 4 megahertz. So that is 4 million in decimal. But that doesn't explain why I'm using 4007500 as discussed in the code earlier. Now I'll explain this value during the code demonstration. Okay, so we've come to this 3 instructions here. Basically, this is to clear the SysTick current value register. And this label here is the SysTick VAL register, which is the current value register base address. All right, that has been assigned much earlier in the program. So it's E000E018 hexa. So this has been assigned to this, and this get copied. This value get copied or loaded into R0. And then here we copy this value, that's decimal 0 into R1. So load 0 into R1. And then this will store the current value of R1 into the address pointed to by R0, which is this address. Basically, that is to store this 0 value into the SysTick current value register. And then here we have a B instruction, or the unconditional branch instruction to main loop, which is this part here. So this will stay in this loop forever. This is an infinite loop. And here is the NDP, the end of proc. Remember, I started the __ main proc earlier. So this is to mark the end of that routine or the procedure. And finally, we'll come to this SysTick _ handler, which is basically the interrupt service routine. And I've called it a procedure or proc. And this is the ENDP, which signals the end of the handler or the procedure. Now, this been assigned a value earlier, so that gets copy loaded here. This is the LED value bit mask for port F bit 2. That is the blue LED on the TM4C series board. Then you read the current data register value. All right, you copy that pointed to by R0 into R2. Then you do an exclusive OR. Basically, this exclusive OR instruction will toggle PF2 or port F bit 2. Then the store instruction will store the modified value into R0, the address pointed to by R0. Here, BXLR, basically, this will return the control back to the main program. Remember, this is a interrupt service routine or ISR. So when it finishes the ISR, it will then go back, branch back to the main program. Demonstration. Now for this demonstration, you will need the TM4C series launchpad board connected to your desktop or your laptop. Okay, so I've got my Kyle IDE running here. I've uploaded my code. So let me just briefly go through the code. So here is the initialization part of the code. We've been through this before. So, and this part here is the register definitions. And here I have the bit mask definitions. And here is the beginning of my main routine. Let's just scroll down. Right. Before going any further, this value here is the 4 million that I've been talking about. I will be using, I will show you how I would change this in a few moments. So at the moment, I'm setting it to 4 million as per discussion. All right. And here is the part where I send it into an infinite loop. And here is the SysTick handler or the interrupt service routine. And here is the end that marks the end of the entire program. Let me just show you my setup. Let me go to my camera, expand it. So here's my board, my TM4C series Launchpad board. And in addition to this, I have, if I will move it gently, this is my logic analyzer. All right, so this is the USB logic analyzer. All right, you don't have to have this. I'm connecting this because I want to show you the output pulse. So let me get back to my board. As you can see, the blue LED is already flashing, but I will build the program again, all right, and download this program to the board. All right, let me bring my camera back up. Let me do a reset. All right, so here we have the blue LED blinking. And now let me just go to the logic analyzer output. Let me clear this, run it again. Right, so just give me a minute to fix this problem. Okay, so I've got the I managed to get the USB logic analyzer to work now. So this is the output from the TM4C series Launchpad board. So if we take note of the on interval here, let me just zoom in. Just give me a minute. You can see that it's giving us 998.400000000 millisecond, which is not what the 1 second that we are looking for. There's some discrepancy, and this is what I would like to discuss. All right, so let me zoom out again. Now, using the Carl Microvision, we are getting a time interval of 998.400 milliseconds. I'm ignoring the other zeros. A time interval of 998.400 milliseconds is very close to the 1000 milliseconds or 1 second that we want. Now, there's a difference of 1.6 milliseconds. Now, for a blink LED application, this minor deviation of 0.16% is unlikely to be noticeable. However, if your application requires precise timing or synchronization with other events, you may need to consider fine-tuning the clock settings or change the reload value. So here is how we can adjust the reload value. First, you calculate the current error. So we have 1000 milliseconds or 1 second minus 998.4 milliseconds. That gives us 1.6 milliseconds. Convert this time error into clock cycles. Now, if the SysTick clock is running at 4 megahertz, as discussed earlier, so the extra cycles needed would be 1.6 milliseconds multiplied by the 4 megahertz. That will give us 6,400 cycles. Now, add these extra cycles to the current load value. So if the current load value that we've got is 4 million, so 4 million plus this 6,400 that will give us 4006,400. So we need to load this value or use this value for the reload value in the code. Okay, so we're back here in the Kyle Microvision IDE. So let me just change this value to the one that we just calculated. So it's 4006400 decimal. Let me save that and then build the target. So 0 errors, 0 warning. Let me download it to the board. So erase done, programming done, verify, okay. Okay, now let's have a look at the board, the TIVA series Launchpad board. And let me just press reset. And we have a blue blinking light. So now let's go have a look at the logic analyzer output. Okay, so here is the logic analyzer output. As you can see, there's a slight improvement. Let me just try to magnify it for you. So it's now 999.200000002 milliseconds. So there's a slight improvement, but it's still not what we're expecting. We're expecting a 1 millisecond interval. So we need to make some adjustment to the reload value. Okay, so we have seen that this value here, 4006400, seem to have got us closer to a 1 second delay. So what I'm going to do is I'm just going to change this to 75. So now the value is 4007500, which is the one that we have seen that I presented in my code at the beginning. So let's see what happens. So if I save it, go to rebuild all targets, everything seems fine, no errors, no warnings. So let me download it to the board. Okay, so it's verified. Okay, so let's go take a look at the logic analyzer output. Okay, so here we are. We are looking at the logic analyzer output. As you can see, we are getting our 1 second delay. Let me just try and zoom in for you. Alright, so we have a exactly 1 second delay interval. And here we are looking at the TIVA C series Launchpad board, and you can see the blue LED is blinking. Hey, so that's it for this video. Thank you for watching, and I'll see you in the next video. Bye!